So what you're telling that the questions that there in the current running course, it's completely different from the previous ones, right?
Just for week number 7, I'm saying.
Okay, just for the
Previous
week
week,
number
it was
7.
not like that. For the previous weeks, like for example, week 1 or week 2 or week 3 or week 4 or week 5 or even week 6, the questions given for the assignment were almost similar to the questions that were given in the previous years. So when you would solve the previous year's questions, we would get some idea of how to solve our.
Okay, okay, okay.
But
That's
the
okay, okay, okay.
week
Understood.
number 7 is an
When
anomaly.
is
In
the
this
deadline for week 7?
week 7, they've asked mainly Python questions and all. We have to download a data set and, they've asked basically programming questions, I feel.
Okay, programming questions. Okay, okay. So Lakshmi, some of the programming questions are there in this week 7 video lecture itself. Did you try to see that? Because programming questions, I am not sure. Like we have to see. Uh,
So yesterday's instructor also, Mr. Sai Krishna, I think his name.
yeah.
He was also solving week 7 of previous years, thinking that like all the other weeks, week 1, week 2, week 3, week 4, week 5, week 6, we will also, our batch will also be having a similar set of questions as the previous years. But even he remarked that, the kind of questions that he is addressing is totally different from our week 7. So week 7 is the only anomaly. All the other weeks, it was fine when you were
So,
solving.
are you like, do you want me to do some programming things? Uh,
It would be really good if before starting the session you could go through what is asked for our week 7, so then you can get an idea of what is actually asked in
yeah,
our.
I'm going through it. Yeah. So you can see my week 7. Yeah. I watched almost all the lectures. If you can see my screen, like, are you able to see?
Yes, I am able to. Yes.
Okay, okay. So let us start from last question. So generate two sample from uniform, the ith element of the target variable. Okay, generate the following basis function. Implement least squares using gradient descent algorithm to predict the target variable b by learning the coefficient vector x. So gradient descent is not yet taught in the class, right?
Yeah.
Yeah, so this is not yet taught. Okay, this I'll take care. But what is the deadline? Just let me see the deadline. 13th. Okay. Shit. Okay, so this is use the least squares to predict the target variable coefficient, which basis function corresponds to largest value in x. Okay. So this we can solve, right? Gradient descent is not yet taught, so I can tell what is gradient descent if you want to me to say. But the first question can be solved uh, using the previous. Like first question is little easy because in that a is equals to what we saw, no, f of j subscript j, or inside it is xi, right? So f, we are writing f as any linear function. Like what is this, 1 plus, suppose polynomial function 1 plus x square or something like that. So which column which basis will corresponds to the highest number, that will be decided if you solve this least squares. So I think f0 f3, oh yeah, you can solve this question. uh, don't need to implement in the Python code itself. And in fact, for the Python code also, some of the examples are given. If you go to the lecture material, I'll go. Uh, yeah, so you can see this lecture material. Lecture, this one, regression 1, regression 2, regression 3, regression 4. So these things are there. Like you can directly copy these codes and try to run. Right, this is copyable. If you understand these particular regression things now, this 1, 2, 3, 4, and this the classification was the very easy thing, like just now I was, but the regression was little difficult. But here you can see, if you want to predict using this degree f, suppose this is there x, okay, this is the x. So what you're trying to do, you are trying to write this x new as the polynomial function, like this is 1 1 1, then x, then x square, x1 square, x2 square, x3 square, third column, then fourth column will be x1 cube, x3 cube, and like that. So if the output variable will be there, like how can I write? I'll write that. You will understand like which basis function will correspond to the biggest, highest value, so that you will understand. And yeah, so again we'll go to quiz 7. Okay, this is the first question. Okay, this is the second question. Yeah, so Lakshmi, uh,
Yes, yes.
uh, if you see this particular thing is already there in this convolution PDF, the lecture is uploaded.
Okay.
Convolution is a classification 1 and 2, because that's only taught about the MNIST data set. One second. Who is there? Okay. So sir only taught about this MNIST data set, and the similar question is there in the class in this. So MNIST data, if you understand these two classification 1 and 2, 3, if I open this, you just try to run these things. You'll understand what is a confusion matrix, or what are the images that is currently classified, true, positive, true, negative. So, and that is also copyable. I was checking whether it is make it copy or not. So, like, are you aware of the Python notebook?
Yeah, I do. I do have.
Ha ha, then
I can
fine.
do it on Google Colab also, right?
Yeah,
Google
yeah,
Colab.
Google Colab. Yes, yes, yes. That's what. That Google Colab will act as a Python. If you have any doubt in Python, so you just let me know. I'll tell that thing also. That's fine. But yeah, what I was telling, these questions are directly similar from those. If you understand these three classifications, sorry, these classification 1 and 2, 3 also. I think yeah, 3.
So you're basically telling that we can refer the lecture
Yeah,
material.
you can refer the specifically this code lecture, because I could see that the questions are there with similar to the MNIST data set, both trained
Oh,
and test data sets. I can understand these questions are not there in the like previous year.
yeah,
So,
yeah,
so that's why you are telling. Yeah, I can understand the thing. So yeah, here also generate the target variable. So you can have to generate it. Once you understand that 3 or 4, I think 6, only 2 lectures are talking about these things. By understanding these things, see, hint, plot the predictions and ground truth. So you have to plot. I also cannot do with pen paper. I have to also open the Google Colab and do the things.
yeah, yeah. Would it be possible for you to do that? Like,
Uh, like
not for
to
this question
ha,
exactly, but for.
if you tell me to do next class, I can do, but this class I have to check. Like
Right, right. Okay, then
I
we.
couldn't prepare that thing. But yeah, I can understand like from where it is. See here also, note you can visualize the basis function ground truth predictions to better understand how the basis function are used to model the linear regression problem.
Hmm.
So here also we have to just plot the things. I feel so. Yeah, I understand that is very different from the very previous year. Download. See here you have to download the autoregressive data.csv file. The target variable is the composition consumption column. Create lag features. Also, in one of the lectures, sir taught about the lag features, creating the lag features. Here, I think lag is last regression model.
Okay, so.
Yes, creating a lag feature is also discussed in the class. You first of all, we need to just copy these codes: regression 1, 2, 3, 4, and this classification 1, 2, 3, 4, 3. Also, convolution demo is not related to this lecture, but yeah, if you want to see the convolution also, you can see. But we have to copy this and we have to change the variables accordingly.
Right, right. So
Yeah.
another query I have is whether such kind of programming questions will come in the examination.
No, it
Or
won't come.
it will come, right?
Yeah, yeah. It's not possible, I guess. But again, I'll confirm with the team whether
Oh,
that is possible or not. But still, it should not come.
okay, then in that case, we can go ahead with this class.
Yeah, okay. Lakshmi, if you want to like particularly have something, yes, you can just let me know before 2, 3 days because today was
Okay,
Saturday. I was doing something else, so it's fine.
right,
Uh,
right, okay.
yeah,
Sure.
yeah, sure. Only you are there and nobody else joined. What is the problem in joining the class? Last class, the recording also was not done properly, and there were not so many students joined. Like, is there any problem related to the class timings or something like that? And are
No,
you guys not aware of the timings or whatever it is?
I don't know actually.
Okay, last class you also did not join.
Last class,
Last
okay, right.
sixth
Yeah,
week.
probably there was another session at the same time or something like that. There was, I'm in Introduction to Machine Learning, this thing
Okay,
also.
okay, okay. So your background is CSE.
Yes, yes.
Okay. So basically in this week, if I go through the lectures, 10 questions, I don't know that Sai is teaching, but it's possible that we can teach the same things. I don't know what he's teaching, but the aim is to give the same lectures only for students for better understanding. That's why two live classes. But we guys are not coordinating with each other. Like you teach this thing, so I will teach this thing. So I don't know basically what he's teaching. So yeah, in lecture 33, sorry, first of all we should go to lecture 31. Recording is on. Okay. So yeah, till now we have seen that what is least square and where least square is used. So revising again that thing like least square is used either for square data, a square matrix, or it can be used for tall matrix. But least square cannot be used for wide matrix. Why? Because there the number of observations are less than number of unknowns in tall matrix, whereas in the wide matrix it is opposite. So that's why that in that case A transpose A is not invertible in case of wide matrix. That's why we cannot use that. And the output expression for least squared we got it as x cap is equals to A transpose A, x cap is equals to A transpose A inverse A transpose Y. So this is least square solution. Okay. So what we're having particularly? We are having experiments, observation, and finally this is causing the data set. Okay. So whenever the x is mapped to y, so that function is associated. So the function is called from Rn to R that y is equals to fx. Okay. So uh, whenever we write this function, the function will be written based on the features that is mapping. You can have several features. For example, you have data set as x, y. Okay, so you have suppose height, you have weight, you have color, you have sex. These things you have. So sometimes these out of these data sets, some features are only important to uh, judge or predict any value. Okay, the y value. So y value is equals to f of x. So f will have these features. So those important features. Sometimes we are having more and more features. So for that only we need to have some of the features. The feature extraction is there in the upcoming video lectures. But in that we are our aim is to write to f. Okay, once we are writing the f, we are converting this f to a matrix A, and using the least square, what is the minimum error, what is the predicted value minus what is the actual value. Then we are writing in terms of least squares. And finally, we are getting as the output. Okay. So this is what we have to guess f from these data points model. Okay, so assume a form of the model, for example, f cap. F cap is a predicted function. Okay, then this f cap is only used for the for writing this a matrix. Okay, so f cap x is equals to alpha 1 f1 x plus alpha 2 x2 x, then alpha p x p. These alpha and alpha 1, alpha 2, alpha and p will be actually the features matrix, feature column. Okay, and these things will be the basics of feature mappings. What can be the feature map? Okay, so y is basically f cap of x. Okay, this is the actual y, the output that we are getting, or the measurement that we are getting. Okay, so these basically first we will start with the linear in parameters model. So prediction error, if we see, what can be the prediction error? So prediction error that we can write using the residual. So suppose this y I of thing is the actual value and y cap of I is a predicted value. So you have to choose this alpha 1, alpha 2, alpha p. Means actually we are fitting the data. Okay. Suppose these are the data. Why we are fitting? Why we are fitting? Why fitting is very important? Because suppose this is the data. Okay. Now if we want to fit the data, suppose we are fitting the data like this. Okay. Means this is fitting the data whole. And these fitting will have this associated alpha 1, alpha 2, alpha n. Okay. So whenever the next data will come, suppose next data is coming here, some here. So you can say this is close to this value. So you can predict actually when the new data set will come. So that's why data fitting is important. And we are doing the data fitting using least squares. Using least squares because how we are doing the least squares, the predicted value should be less than, it should be very, the error between the predicted value as well as and the actual value should be the minimum. In that way, we are fitting the data set. Okay. So I hope the motivation is clear. So, so this is the residual. Now choose the parameters listing such that this particular residual for every data point is minimized. So first we will see the matrix notation. So matrix notation is nothing but suppose x 1 x n are the n r n vectors, n vectors, and this y 1 by n are the belongs to this r, because anyway the function is from r power n to r, right? Because anyway the function will be something theta plus bx plus bx square b1x squares, like that. That will be a polynomial function. Different types of function will be there. Okay, so this is the data set and this is the prediction value. Now we are trying to minimize this particular thing. And so yeah, aij, that's the only thing that I was telling about that thing. How you can check which particular basis function, this is the basis function, right? This is the basis function for this particular feature. This is the basic function for this particular feature. This basic function for this particular feature. So these are the fitting variables. So how can you check which basis function is the most important? How can you check? Using alpha values, right? For those basis function where alpha is the highest. So first question was based on this. For, highest. That basis function will be the answer. But because we are giving the importance to the basis functions. For example, the basis function f0. Anyway, we are writing this f cap x is equals to alpha 1 f1 of x plus alpha 2 f2 of x plus so on alpha n x of n f n f x. Okay. So if this is the most important, this associated weight parameter should be very high. So if you are trying to find this alpha, so how will you find the alpha? Alpha you will find through this least squares, right? Anyway, that alpha, this alpha is alpha 1, alpha 2, so alpha n. And you are finding through least squares. How you are finding? A transpose A whole inverse A transpose Y. Once you find this, you'll find the alpha. Whenever which value alpha k, so k basis function will be the answer. Okay. So this is alpha least square. So that's what I was trying to tell. This is the answer. Okay. How you can find this alpha cap least square of A transpose A whole inverse A transpose Y, provided the column of A are linearly independent. So yeah, this can be possible in tall matrix, because in tall matrix you are having these things. The columns of tall matrix are also linearly independent. That's why this can be possible. Whenever this wide matrix is there, that is not possible. Why? Because columns of wide matrix are linearly dependent. 100% sure. Or also, A transpose A is not invertible. Sometimes when I used to study, I used to have confusion why this is not possible for wide matrix. What is the reason, and why in case of wide matrix we are using right inverse. So this type of answer you should have in your mind every time. So wide matrix के time पे we are using A transpose A transpose Y. Okay, we are using, this is least norm that will be there in the future classes. But yeah, this is least one. Now, in case of white matrix, this AA transpose is always invertible. Okay. So, sir gave example for fitting with the constants. So, suppose we are having only one value. So, f11 of x is only 1. So, this is actually used for bias. Okay. So, in practice, it is used for bias. So, if it is 1, so how you can write? You can simply write this A transpose A whole inverse A transpose Y, and finally you are getting this as an average value. Okay, and this is basically the interpretation of this thing. Okay, so if you want to fit the straight line, so you can see this is a simple constant. Okay, f is equal to 1 means simple constant. Now if you want to fit the straight line, so let's take two basis functions. So f1 of x is equals to 1, f2 of x is equals to x. So this is why I hat of I is equals to alpha 1 plus alpha 2 x of I. So that is A is equals to 1, 1, 1, and then x1, x2, xn. Okay. So in that case, you can directly find it. So again, that will be again this A transpose A whole inverse A transpose into Y. So if you want to fit the polynomial, so you will have so many basis functions, but the basis functions will be this type. Uh, f1 of x is equals to 1, f2 of x is equals to 2, f3 of x is equals to x square, then fp of x is equals to x power p minus 1. So this is actually ordered p polynomial. Okay, in that way you are fitting it. Okay, so this is this least square estimate of model parameters. Here it is how this matrix A is built. You just have to understand it. That is very important. So you can see this is 1, 1, 1. This is the basis function, and this is also called as Vandermonde matrix. So in the later classes, in the few upcoming classes, we will see the sensitivity analysis of this Vandermonde function matrix. The how this sensitivity analysis will be different. That will have to calculate this condition number, and also this condition number is not that good for this particular matrix, so this name should be important, that you take to care, you need to care. So I think this is very easy. This is straightforward. And then going to the lecture 33. So lecture 32 was basically on the programming session. You need to, sir only gave some institution insights on that uh, programming, whatever he has done. You just have to copy paste and try to understand like what you have done. Moving to the lecture 33, it is a problem for classification. So till now we saw that we are mapping, we are doing everything, the least square things for regression. Okay, regression means you'll have, what is a regression? What is the difference between regression and the classification?
Regression will have continuous outputs like numbers, while classification will have only discrete outputs,
Yeah, very,
like
very
whether
good. Yeah, yeah.
scale possible.
Discrete outputs and number of classes, fine. So you're fitting the data, and whatever, suppose the data set you're fitting is one real line. So output you'll have so many, and it can be many values, many real numbers. Okay, y belongs to r bar n. Okay, but here in case of classification, you only have the binary classes or discrete outputs, k classes or discrete outputs, whatever it is. So the least square needs to be changed. Okay, because until now we are saying we are just getting the error and we are trying to minimize that error. So we can't minimize the error, particularly when we are having this -1 and 1 as our output. Suppose we are talking about the magnetic class. So what we're trying to do here, we are having these things as a, so one more thing is supervised and non-supervised.
And
Unsupervised, yeah. So here in the classes till now we are only talking about the supervised. So in unsupervised we are trying to find the pattern in the data and
oh, there's
then
some issue in my network.
hello.
Yeah, yeah, your voice was, muted for a little while, so I thought it was some problem in my network.
Okay, okay, no
Now
issue,
it's
no issue. Yeah. So like you are already attending the introduction to machine learning. I think that
yeah, yeah.
so might know about the unsupervised and supervised. No, so
Yeah, correct.
basically, yeah.
Supervised means the inputs have a label associated with them. Unsupervised means they don't have any label. And
So can you give me
so
some
unsupervised
examples of unsupervised?
clustering and association and super clustering you
So
like
here also we are doing clustering, right?
supervised learning. Uh, no, like basic thing is that inputs will not be labeled in unsupervised, but in supervised inputs will be labeled.
Yeah. So support vector machine is actually the example for unsupervised. And classification is also there that came in clustering. That is unsupervised, but this normal clustering is actually supervised because even here we are having the data like +1, -1 or whatever, true, false. Suppose we are having here as a true, false, +1, -1. So how can we map it? How can we find the proper classifier using least square? That is a problem statement. So basically we are trying to convert the function that the mapping function that we used it previously in the linear square into the non-linear function. So how we are classifying? So here the f cap, this is the main thing, that this is the f cap is not direct function. Previously this f tilde was r power n to r, but here this is f cap. So we need to convert this f tilde to f cap for the classifier. Okay. So this is the data set, and here the y is equals to fx. So we know that f cap is equals to this f alpha 1 f1x plus so on alpha p f fpx for this p basis function. Okay, so we need to estimate here this all the functions are from x to x -1 to 1. Okay, so we need to estimate the parameters so that the model predictions or the label predictions by the classifier match exactly as we know that it should match properly. So if we see the confusion matrix is important. What we are trying to minimize it. Okay. So we can have true positive. Suppose we are having the true label as +1 and we are getting also +1. So this is true positive case. And suppose we are getting true negative. Means suppose you have true, you are getting as output as negative and also getting the prediction as negative. So this is true negative. Whereas this is opposite. So true positive, true negative, false negative, and false positive. So how you can just do the confusion matrix? You always remember this is true positive, this is
True
false.
values,
Yeah, hello. Yeah,
actual
seriously.
values, the rows and the predicted values as the columns, isn't it like that?
Which one? This is confusion matrix. This is all different. Here
Yeah,
we
what
are
I'm saying
trying to
is,
analyze classification. What is classification? We are trying
yeah,
to.
yeah. I was just trying to add, saying that in the confusion matrix, we always have the actual output on as the rows and the predicted outputs as the columns.
True, true, true. Very true. Yeah, yeah. Yeah, this is true. So yeah, this is false like but basically the diagonal elements are positive, always correct, and you are trying to minimize the summation of the off diagonal elements. Okay,
Right,
yeah.
right. Okay.
So the what will be the error rate? The error rate is
Error rate, all the
uh,
non-diagonal elements divided by
total
everything.
number of points. Yeah, yes, yes. So this is error rate. So we need to minimize this particular thing. Okay, this is our aim. Basically, now we are coming back. This is all about the classification, like what is classification and what is true positive, true negative. Now, least square classifier. How can we design the least square classifier? So we have to choose the basis function similar as before in the regression least least square regression problem. Then we will convert that to using a sigmoid function later for the classifier. So we are having this unknown parameters because we need to fit it. Okay, that needs to be estimated. So this f tilde, this is similar or same as least square regression. Okay, this f tilde of x is nothing but alpha 1 f1 of x, so on alpha p of x. So it will have all the values belongs to r power n. Sorry, r. Okay, again this is if you convert it from matrix, then r power n. Okay, so this is the model real values. Now you need to minimize this, uh, minimize alpha 1 alpha p summation y of minus f tilde of xi square. Okay, so this we have to choose a classifier that is least square classifier. Okay, this is sigmoid. How this is works, because this is giving only two output. This is plus one, this is minus one. Okay, so whatever value it is getting, suppose f1 of f xi, suppose this is giving you f tilde of x1 of 2.4. So this f cap of x will be giving you 1. Okay, because this is greater positive values will be giving 1. Suppose this is negative 2.4. This is will be giving minus 1. So in this way, you are converting the every real value to a classifier plus 1 and minus 1. Okay,
Okay, okay.
yeah. So and now this f cap will be the output predictor value, and in this way you can directly design a classifier. Okay, in the end, you are just converting this to this particular thing, and you are designing the classifier. And in general, this f tilde of x is simple linear fit or regression model. Okay, the same examples I gave here. Now, what we will do in case of multi-class? Like, any idea, Lakshmi?
Multi-class problems. Okay, so the confusion matrix is again k by k.
Yes,
And
yes.
the non-diagonal elements represent the misclassification, and the diagonal elements represent the correct predictions.
Yeah. So, how can we design this? See, in case of normal classifier, two class classifier, we can directly do using sigma. Now, how can we do it for k classes? Because anyway, we want this f cap, right?
Right.
And
So,
our aim is to find this f cap.
um, so for uh, take so for see there are k classifiers, and consider each classifier as a two-class classification problem. And
Yes, yes.
yeah, so
Then
f1 tilde. So for f1 tilde, uh, we'll also have like plus one if it's less than more than zero, and minus one if it's less than zero. F2 tilde will also be like that.
okay,
Similar.
okay. Nice approach, but yeah, there's a little twist. So here, what we are trying to do, we are just taking one f cap. Okay, but previously, what we will do for here previously we used to do this f tilde because only two classes are there. But in case of k classes, we will try to divide into k labels. Means the first label means it can have plus one, minus one. So it will be designed using k2 class classifier. Okay, you understand this thing. Second label,
Yeah.
it will have plus one, minus one. Similarly, k label, it will have plus one and minus one. Okay, so this is f tilde of x, this is 1. This f tilde of x, this is 2. This is f k of x, this is all. Okay, so and in the end, suppose this is giving you, we will see with example, this is giving you 2.4. This is giving you minus zero point 0.4. This is giving you 3. Okay, so in the end, uh,
You
after
take the argmax. You take the argmax of
Y-
all the f
Yeah,
tilde. So
yeah, it will be argmax. Why? Because this is giving confidence. This value is giving confidence. This is will be plus one. Okay, anyway, it is greater than one, zero, and this is giving negative, so minus one, and this is plus one. But if you compare these two, which one will give you more confidence? Obviously, this one. Okay, so this f
yeah,
tilde of x in this case for the k classifier, it will be argmax of k, where it will be 1, 2 till k
right,
f tilde of x. Here you remember this is k,
right.
or this is k. So in this way, this is classifier. So yeah, Sir also did the same thing. So
Yes.
this is r max of f tilde of x. So this is f tilde of x. Yeah. You just have to identify how to write notation properly. Once you understand these things, right? So you can coding is just a way of writing in the notebook. So that is fine. So this
So let me just understand one thing. So here you got fk tilde was 3 and some other value was 2.4. So because 3 is greater than 2.4, you're taking yeah, like plus 1 as the final output. Suppose we got suppose it was negative values, like one was minus 2, something else was minus 4.
yeah, again that maximum value will be taken because that
So
will give.
minus 2. Minus 2 is the maximum value. So then it will be still classified as minus 1, right?
Yeah, yeah,
Okay.
yeah.
Okay.
But because that will give more confidence.
Right. Right.
So moving to lecture 35, I think lecture 34, sir only gave intuition on the coding part. So two lectures are there for the coding. So and I
Yeah.
think almost all the questions are there from that coding perspective only. So
Yeah. Thanks.
yeah, so that's strange. But yeah, okay. But only you if you understand this theoretical thing, then only you can map to the coding.
Right.
So now the last part of the theory is what is a constraint optimization? What is a constraint linear least square or the least square? So in one of the example, I'll just tell with the example. So what happened in one of the example, uh, we are having these fitting points. This is this. Okay. So what happened? Sometimes this is non-linear function. Okay. Sometimes we need to fit this particular curve. This is the data points. This is the data points. This is the data point. We need to fit this curve using piecewise linear functions. Suppose this is a one function, this is one function, or this is two functions. So what I'm trying to do, I am dividing the data set into three parts. Okay. I'm trying to divide the data set into three parts, and this is the actual and what I want to do. I want to add these linear functions so that I can write this particular thing, this fitting of data point using three piecewise linear functions. Okay. So what will be my aim? Why I want to do this? First of all, non-linearity affects the system stability to a large extent, and furthermore, this this piecewise writing in a piecewise linear function or the linear functions, we can stabilize the system. Or I think if you are from E background, the LTI, you can do this LTI system analysis or something like that. So this is the aim. So you are dividing the data set into three parts based on the range, and then you are writing for one function, the second function, and third function. Okay, and now whatever the first function f1 of a should be equals to f2 of a. Okay, and this is f1 x, this is f2, this is f3. Also, this point is a. Okay, this point is b, and f2 of b is equals to f3 of b. This is our constraint. Okay, that we need to, and we also want to fit the data. So fitting the data is also coming from least square. Okay, and also we want to fit the data using piecewise linear functions. So these should satisfy. Moreover, on top of it, we also want the derivative of f1 of at a is equals to f2 of a, or no, f2 of b is equals to f3 of b. So for these type of thing, we are going to constraint least square where we are having constraints also when we are doing the least squares. Okay. Also, at the same time, we also want the error should be less, so that it should properly fit the data. Okay. So again, as we know, this is the least square. Minimum of r belongs to r, x belongs to r power n, mod of ax minus b whole square subject to cx is equals to d. Okay, so this a belongs to this thing, b belongs to r power m. This is a constraint least square because here these cx is equals to d, where c is the matrix and d is actually the output. This is actually coming from the constraints of these four. Okay, this is 1, this is 2, this is 3, this is 4. So 4 constraints are there, then the c will be uh, what will the matrix size of c? P. P means number of constraints into P cross P. 4, 4, 4, 4. No, sorry, D. P cross X value. So whatever the X of data set is there, suppose uh, X have n data points, so P cross n. So here, suppose we are having P is equals to 4, and you're fitting the alpha values as alpha 1, alpha 2, alpha 3. So the n is equals to 3. So C will have size of P 4 cross 3. Okay, like that you have to understand. And D will have the size of n cross 1. Okay, so because anyway this is multiplied with x, so you should make sure this x 3 will be similar to the dimension of x. Okay, so at the end, what we want, what is feasible solution or what is optimal solution? Okay, the feasible solution is as a feasible which will satisfy and constrain these things. Okay, if it's satisfying the constraints, then it will be feasible solution. What is optimal solution? The optimal solution is the one where at every point, whatever the output is there, whatever the actual value that you got by solving this least squares, at norm should be less than the other x, other optimal values of other x belongs to r power n. So the norm should be less, or this particular thing should be minimum. Okay, that is optimal. So almost this is similar, but this is different. We always go for optimal solution, not feasible solution. Feasible can be anything that is in the range, but optimal means you should find the least norm. Okay, that is the our aim. Okay. So again, sir gave two examples. That is these things called spines. That I also gave the example of this linear function. That is not called spine. That called linear fit. Okay, but this polynomial functions are called five spines. This green color and the yellow color. Okay, so you are dividing the data set into two parts. This particular range and the another particular range, and then you are trying to fit the model. Okay, so suppose we are writing this f cap of x into two functions, p of x plus q of x. P of x is this green thing, or q of x is yellow thing. A green thing is for all the x less than or equals to a, because you are dividing into a, and q thing is for all x greater than x a. So conditions are again that what I told, p of a is equals to q of a, and also derivatives of polynomials should match at a. Okay, the same things. So what is the prediction error? The sum of the squares of the prediction errors. So you are dividing the yi into two parts, yi for p of x and yi for q of x. So summation of this all the whole function p1 of x minus prediction value and q1 of x. This is p of x and this is q of x minus prediction value. Okay, so how can we write the data point? Data, this is theta that we need to find. Okay, and this is a. So This is A, how we are writing this A. This 1, 1, 1 will be the bias vectors, and this is alpha 1. So, okay, this is alpha 1. So, xi of 1, xi or square of 1, sorry, so xi of q. Again, it will be different, 2, 2, 1, 2, 3, and on, based on these. I hope this is clear. You can write like this. How you can write? Here the values are 0, so 0, 0, 0 till the points of A, till this points, okay. Then again it will start 0, 0, 0, and then it will start 1, uh, x1 of 1, then x2 of 1, this things, beta. So again, a theta will consist of alpha and beta, both. Alpha for first function and beta for second function. Okay. So we are trying to minimize now this, but we are also having the constraints. Okay, we are having the constraints, these things, first constraint and second constraint. So how you can write cx is equals to d, that is very important. So writing the first constraint, you can write this in the form of matrix. How you can write, you are having 1 a square aq, because here you are having alpha 1, alpha 2, alpha n, and also negative is equals to 0, so that's why negative points. Okay, and if you are writing p derivative is equals to q of a, q dash of a, so how can I write, alpha 2 plus 2 alpha 3a plus 3 alpha 4a square is equals to beta 2, this like this. So overall you can write like this. You can write like 0, 1, 2a, 3a square, 0, minus 1, minus 2a, minus 3a square. Okay, okay, and this is also what? Alpha 1. These things, okay? Alpha 1, alpha 2, so on. Beta 3 or beta 4, okay. Now you're appending the matrix, first one and the second one. So that is the whole C. That is represent the whole constraint. So this is C. This is you are writing like 1a square and like this. First for this and second for this. And this is alpha is nothing but this thing. Alpha and beta. Alpha vector and beta vector. This is written wrong. Okay. So this is the least square. This is constraint least square. You are minimizing this thing subject to Cx is equals to D, where Cx is equals to D is representing the constraint for the problem. Okay. So whenever this is very similar to least norm solution. So what we are trying to do here, least norm solution is one of the example for constraint optimization, where we are minimizing this mod of x, because in least norm, where this term for least norm comes into the picture, uh, Lakshmi, when we do the least norm.
Is it for like the regression, the lasso ridge regression? Is
Uh,
that no?
no,
But it's
give us a simple example where we do the least norm. See,
can you give a clue?
we are doing this least square for what?
Yeah.
Square matrix or tall matrix, right? Why
Yeah.
tall matrix? Because we are having
Because the columns are
equations.
linearly right.
Equations more than unknowns. Okay,
Variables. Yeah.
but least norm will apply to wide matrix.
Okay.
How? Because in this case, equations are
Equations. Yes.
unknowns. Okay, now
Yeah.
let's see what with the example. X1 plus x2 x2 is equals to 3, x1 plus 2 x2 plus x3 is equals to 4. Okay, x3 is equals to 2 is just 3. Now you're having 2 2 1 1 2 1. Okay, this is x1 x2 x3, 2 cross 1 and 3 cross 1 is equals to, this is 3 4. Okay, so what I'm trying to do here, whenever we solve this problem, so we are getting output as infinitely many solutions. This is very important to realize, like where we use it. Now we are getting infinitely many solutions. Why? Because we are having more unknowns, more
Yeah.
unknowns and less equations.
Yeah.
So suppose we solve for x1, x2, but we can easily make guesses for x3. So you'll have so many solutions, infinitely many solutions, where you can make guess and all. Okay. So this is actually not intersecting, but yeah, parallel lines. Okay, you are having parallel lines. Intersection means simple solution of the equations. Okay, but here in both the cases, uh, tall matrix and right matrix, you are not intersection. In tall matrix, in fact, you are intersecting for a particular case where all the columns are linearly independent. For wide matrix, all the uh, lines are not intersecting. Okay, so here you are having so many solutions, so many solutions, x1, x2, x3 have so many solutions. Now you need to pick up one solution. Suppose you want to have a best solution. So in order to find the best solution, our aim is to find best solution. Okay. So in order to find the best solution, we minimize. The best solution will be pair or x vector such that it minimizes the energy. This is 2 norm, this is square, such that ax is equals to b. Okay, so we need to find this, and this will give you 1x, right? This will give you 1x. So from here, the least norm comes into the picture. This is least norm. Okay, now you're having several sets of solutions for x1, x2, x3, but you need to find it one solution or the best solution which minimize the energy such that ax is equals to b. Also, we know that you are having set of possible x1, x2, x3. It satisfies these things, right? So, but you need to find this x. So, this is the example of our least square. Okay, where cx is equals to 3. So, sir gave such example like when when least squares become the least norm problem, when a is equals to I and b is equals to 0. So, when a is equals to I and b is equals to 0, the least square turns into the least norm. Okay. So, but this was a particular case for wide matrix where we are having infinitely many solutions. We want to find the best solutions. Okay. No, now solution to the constraint least square. So basically, what we're trying to do here is minimizing this x belongs to R power n, ax minus b power square, and here we are doing this ci x is equals to di, as this is the constraints. So these are solved using Lagrangian function. So this is a particularly part of KKT condition. So sir introduced this KKT condition here. So how can we write this Lagrangian of x or L of x of z? So this is nothing but the same function plus z1 ci. This you are writing this as a left part. You don't write like this. This is di minus ci dx. This is wrong because this zi, all zi are greater than 0. In that case, zi will be less than 0. Okay, if you write opposite, that will that will change the whole perspective of the question uh, that you are solving. Okay, and if you are finding this is a Lagrange multiplier, and there exists this x cap is the solution to the constraint least square if there exists z cap belongs to R power p such that these things are 0. Okay, so on top of it, KKT condition states that these will be optimal if and only if this particular matrix is invertible. So how we have written this particular matrix, I'm just telling. What I'm trying to tell, once you write this Lagrangian and you're equating it to 0, you're getting a particular matrix form. Okay, and finally, if you equate it to 0, and by solving this particular thing, right? Okay, the derivative of this thing, this S cap will be the optimal solution, satisfying all constraints. Okay. Anyway, we are inducing the constraint problem using Lagrange multiplier. Here it is Z. Okay. So if you're differentiating L the dou all dou xi, okay, and you are equating it to 0, these equations in matrix form can be written as this one. Okay. Then if you see the optimal condition in this particular matrix is also called KKT matrix. Okay. So using KKT condition, the constraint least square solution exists is the KKT matrix is invertible. Okay. So if this particular matrix is invertible, then only we can have this uh, as a solution, as the optimal solution, or the solution exists for this particular problem. So if KKT matrix is invertible, if and only if it has the linearly independent columns, as we know that. Okay. So again we are just checking with the A is equals to I, B is equals to 0, because that will convert it to least norm. Okay, as we saw it previously. So if we convert this A is equals to I, so A I transpose I is equals to I only. So here I, C transpose C 0, and then if you do this, so finally the output you are getting as C. Least now the C transpose C transpose whole inverse into D. That is right inverse multiplied by output variable. Okay. So I hope this is clear and this is very interesting. I think that KKT condition may seem for you to not interesting, but this is interesting. The KKT condition is nothing. So you have to write in the form of the Lagrange, and once you write in the form of Lagrange, you can just check the particular matrix, the KKT matrix that is forming is invertible or not. So if it is invertible, then fine, you can go ahead and find the solution. And again, we converted the least norm to a least square to least norm by putting the particular value of A is equals to I and B is equals to 0. Okay. So this was enough for theory part. Now we will go to the Lakshmi, do you have any doubt?
No, no. Please proceed.
Yeah, okay. So we will go to the questions. Lecture 7. So sorry, I should remove the solutions. Okay. The first question states that let A be a matrix with linearly independent columns and X cap denote the least square solution to AX is equals to B. State which of the following statements are true. This is very easy question. So what can be the answer? If AX always equals to B, option 1. If AX is not necessarily equals to B, option 2. If X cap is equals to 0, then B is orthogonal to the columns of A. So this is
Can you,
obvious.
yeah, can you explain C how if X cap is equal to
Yeah,
0 then
that is only thing that I also So answer is D, both B and C and correct. How it is? So let's see that. If X cap is equals to 0, then B is orthogonal to the columns of A. So X cap is equals to B. AX is equals to B. We are trying to say X cap is equals to 0, then B is orthogonal. How it?
X cap is equal to A transpose A inverse A transpose B. So
Yeah,
if that is 0, it means, what does it mean?
okay. If it is B is equals to 0, sorry,
No,
X is equals to 0. Okay, okay. This is 0.
this whole thing is 0, yeah. So that's, how does that make B orthogonal to A?
Wait. B is orthogonal. So orthogonal. Okay. Got it. So do you know the orthogonal property? Like here, if you are having uh, Sorry, what is this? A transpose B. These are simple inner product, okay? This A is a
Okay.
vector, B is a vector. If it is 0, so what we write? Cos of theta is equals to A transpose B divided by mod of A, mod of B, right? If it is 0, then theta is equals to 90 degree. Okay. Similar case
Okay.
here, uh,
Ah,
this particular thing, this A transpose A cannot be 0.
0. Okay, okay.
So A transpose B is 0.
0. Okay, fine. So that means A is in, also going to
Ha,
be.
it
Right.
will, and here it is matrix. So A1, A2. Okay. So all the columns
Right.
again. So this will imply A1 transpose B is equals to 0. A2 transpose B is equals to 0. Similarly, A transpose B is equals to 0. So all the columns of A, B will be orthogonal.
Okay, got it.
Yeah, I
Thanks.
don't know what is written here. Anyway, we can ignore. So yes, we have to find the value. Okay. So let B is equals to alpha 1 x plus alpha naught. Determine for what missing value of B will the residual error result in 0. How can you find this?
6 to 7 times 3 because B is just 3 times of X.
Is it? B is 3 times of x, you are telling. No, no, no. We are trying to fit the value B is equals to alpha 1 x plus alpha naught. You need to find this alpha 1 and alpha 2, and then you have to fit it.
Okay.
Because you are doing ax minus b. Residual is what? A
Residual
aix
is
minus b, right? But here nothing is ai and
like just by observation, everything given in the B row is 3 times what is given in the X row. So,
okay, okay. Simply so here, so I was trying to map this using least square. This is a very simple math problem. Okay. Okay, that is not related to least square then. Okay. So simply it is 3 times, so we can write this like this. Okay, this is a good question.
yesterday Mr. Sai Krishna PMS, he also solved exactly the same questions. Same.
Okay,
So the
okay.
we solve this will be a repetition. Can we take some other questions?
Okay, okay. So basically, our thing is not like that we can't repeat the same things. Just his part is like first is on Friday, I guess, and mine is Saturday, and we are asked to solve the same set of problems. Uh,
Oh,
from where I can make the problem, that is also the the tricky part. Uh, like so, and we are strictly informed not to solve the current problems because that is your thing. So yeah, so we will just quickly go through and then I'll end the class because anyway we covered uh, all the things for the theory. If you have any problem with the theory, just let me know. And if you want me to see go through the week six also we can go through, or else we can just leave the class. That is fine. Week six, like, do you have any problem week six? Week six is already left. Okay. So I just saw the problems of week six. So it is just how we can find the solutions. It's A transpose A ka whole inverse into A transpose B. And if you go to the second problem, so what can be the answer? This invertible matrix, as we covered this quite a time, quite often. So this is again the condition number. What shall the following are the highest condition number with respect to induced to now of the matrix? How can you solve this problem?
condition number of a diagonal matrix is biggest value in the diagonal divided by smallest value in the diagonal. So in that case, A, 10 by 1. That is the biggest condition number of all the matrices given here.
Yeah, that is fine, but you can just maximum magnitude of A or minimum magnitude of A.
Yeah,
So maximum magnitude is 10, minimum this 1.
yeah.
So using this particular formula, you can find.
Mhm.
So this is Frobenius norm. Uh, this is uh, sometimes whenever we try to minimize this whole matrix thing, then we are minimizing the Frobenius norm. Okay. The least square will be converted into least uh, least square using the Frobenius norm. Do you know the difference between Frobenius and normal norm?
Yeah, Frobenius norm is square root of all the elements of the matrix, mod of that squared, sum of all the elements of the matrix mod squared,
Yeah,
and
basically,
both.
if I write this, suppose this is A1, A2, all these things. Okay, these three columns are there. Okay, so if you convert the whole matrix into one stack, one vector, this is C1
Yeah,
vector, this is C1, this is C2, this is C3. So if you are writing like this, C3 vector, so if you sum it square Ci, then this is once it is converted to a vector, then you can write like this. Okay.
okay, and under root, right? Whole thing under root.
Uh-huh.
Whole thing under root, square root of
Yeah, yeah, under root.
sum of.
Okay, okay, okay. Sorry. Yeah. So we always like if you write like
That's
this.
Frobenius.
That's fine.
Okay, and other norm is like norm one is just the sum of the columns. Yeah, sum of the columns. Mod of the values of each column.
Yeah, yeah.
Max of the
Yeah.
sum. And infinity norm is mod of the sum of the row
The
values.
infinity norm
Max
is maximum of
row sums.
no maximum of all the elements of the entry.
Okay.
Yeah, maximum of the all elements of the entry of any vector. And what is zero norm?
Zero norm is one.
The zero norm is actually the number of non-zero entries that is used for sparsity.
Uh-huh. Okay.
Okay, so this was the easiest part, like true, false, and some of the questions are there. Uh, so you are telling the same things like he also taught, but if we have different things, suppose this is more perturbed by matrix, different matrix, so that this will be acting as a different matrix. Okay, so here this is A transpose A is actually WA and B is actually WB. Okay, so in some cases this W is very important because we need to convert a matrix into proper form, because here you can see this is actually the weight matrix. Okay, so you are trying to assign a weights to a particular values. So the particular values is nothing but we are scaling by zero point 0.5, so that's why this WA is changed. So if you write like A transpose A whole inverse into A transpose into B, so you can write like WA whole transpose A trans inverse into A. A is nothing but WA. This is okay. So sorry, my tablet is not charged. So okay, I think you have some intuitions. So next class I can see what type of problems are there in the present thing, and we can
Right.
see the things.
Okay. Okay. Thank you. Bye.
Yeah. Okay.
you.